Hi everyone, in this tutorial I will show you how to model the temperature distribution of a water-cooled induction heating coil using Comsol Multiphysics. This is a multiphysics problem which can be solved in 3D, and we will need three physics interfaces for it. So the first one, under AC-DC module, go to electromagnetic fields and choose magnetic fields. The second one will be from the CFD module, so go to fluid flow. Under single phase flow, choose laminar flow. And under heat transfer, choose heat transfer in solids. Okay, I will add an empty study. I will add the steps later on. Okay, it is loading now. So I will change the units to millimeters. Let's define the frequency. The operating frequency will be 200 kilohertz. So the coil will be supplied with a sinusoidal input current. And due to the current, the coil will heat up and we need to cool it down using water, which will pass through the hollow copper coil. To construct the coil, go to Geometry and insert a helix. We'll keep the number of turns to be 3 to minimize the size of the model. And then the outer box for the air domain. Okay, now we need to make the coil hollow with some thickness. So to do that, I will insert a work plane and attach it to one face at one end of the coil. So insert a circle, and the wall thickness of the copper coil will be 0.3 millimeters. So you can zoom in to see it. Now let's exit the work plane, and this face needs to be swept along the coil. So insert a sweep operation, choose the circle of the work plane, and then choose one of the edges of the coil. Now we need to accurately compute the power loss in the coil, the voltage and the input current, which means we either need to have a closed loop, which we don't have in this case, so we need to connect the ends of the coil to the outer boundaries of the air domain. So to do that, we can insert an extrude operation and select the ends of the coil. And then we will extrude this face to the outer boundary of the air domain. Select any vertex. So this is another way to obtain a closed loop in Comsol. And now for the other face. Extrude. So this is the entire geometry. We have the air domain, we have the copper coil and the hollow region within the copper coil through which the water will be flowing. We can go under definitions and make some selections. explicit selections, which will make it easier for us to select the same boundaries again and again in the physics. So let's define the coil and water combination. It's basically everything except the air. And let's select the coil. The water section. And lastly, the outer surface of the coil. So that's a boundary. This is not really necessary, but it makes it convenient to make the same selection again and again in the physics interface. So you won't have to manually select all the boundaries multiple times. Okay, it seems that I selected all the boundaries. Perfect. Now we can go to materials. From materials, we will search for water. Okay, and we will select water liquid. Two magnetic properties are not defined here, so the permeability will be 1 and the relative permittivity will be 80. And for electrical conductivity, a very small value is given. I will change this value to 1 because this will improve numerical stability. You can leave it as it is, but it doesn't make a difference because 1 is still a very low value. It's still an insulator, electrical insulator. So, but using any value which is not very close to 0 improves numerical stability. The other material we need is copper. Oh, and I forgot, for water, we need to change the selection to water. And for copper, we will choose coil. You don't need to insert the dynamic viscosity because we will not model the fluid flow for copper. And we also need air. The relative permeability is 1, electrical conductivity 1, relative permittivity 1. Now the cross sign means that some properties are not defined, and we don't need to define them because I will unselect them in the physics. So the magnetic field interface will model basically the whole geometry, but for the laminar flow, we will select only water. And for the heat transfer, we will select only coil and water. So if you go back to materials, you see the red cross is removed and all the necessary material properties are defined. So now we can start building the physics. In the magnetic fields interface, go to physics and insert a coil node. Select coil. And we will keep it as a single conductor, which means the skin effect will be taken into account and the proximity effect will also be taken into account. The coil excitation will be voltage with an amplitude of 30 volts. But because the electrical resistance of the coil is very low, the amount of current that will flow in the coil will be very high. Under geometry analysis, we need to select the input and the output of the coil. So that's a surface or boundary. Right-click on geometry analysis and insert an output node and select the other end of the coil. And click on magnetic fields and go to discretization. I will change the magnetic vector potential shape function from quadratic to linear. Because with quadratic, a lot of computer memory will be needed to compute the solution. So I will change it to linear, which will not affect the accuracy by much, as the mesh will already be very dense in the coil to compute the heat transfer accurately. That's all for the magnetic fields interface. Now we can go to laminar flow and insert an inlet. This is where the water will be entering the coil. And we will select the boundary condition using mass flow. So in reality, you will be connecting it to a small pipe, which is immersed in a tank of water. A small pump immersed in a tank of water. And you will know how much the pump can output. So in this case, I will just assume that the output will be 10 ml. The volume is 10 ml per second. So we will multiply that by the density of water, which is about 1000 kg per meter cube, multiplied by 10 meter cube, and to convert it to ml, I will divide it by 1 million. Okay, meter cube per second, the volumetric flow rate. So that's all for the laminar flow interface. Now we can go to heat transfer interface, and we will insert a fluid node for the water. Select water. And under the velocity field, this will be taken from the laminar flow interface. So change user defined to velocity field, and you can see SPF, which comes from the laminar flow. And from boundary, we need to have an inflow. Again, this is where the water enters the coil. And we will assume the temperature of the water to be just room temperature, so 22 degrees Celsius. And we also need to define the outflow, where the water exits the coil, which will be the other end of the coil. And then I will insert a heat flux node to model the natural convection. So select convective heat flux. The heat transfer coefficient for air will be approximately 10 watts per meter square Kelvin. And we will select the coil surface. It's named explicit 4. Let me rename it as coil surface. And we will also include the thermal radiation. Again, select coil surface. The thermal emissivity of copper will be about 0.05. It's a very low value. The ambient temperature will be 22 degrees. So the radiation, convection, and heat transfer to the water. That completes all the requirements for the heat transfer interface. Additionally, this is an option. You can go under multiphysics, you can insert non-isothermal flow. So this node will take into account the change of properties in the fluid due to any temperature change. In this specific model, the temperature change of water will not be very high. In fact, it will be insignificant. So adding non-isothermal flow node will not really change the final result. And now we need to build the mesh, a user-defined mesh. Insert boundary layer and a mapped mesh node. So for the mapped mesh, we'll select the boundary at which the water enters the coil. And we will insert a sizing node. For the boundary layer, we will need two nodes. So the first one is to take the skin effect in the coil into account. So change the selection to boundary. Select the boundary of the coil. And in the layer, select the outer layer. I will use 3 layers with a thickness. The thickness of the first layer will be 10 times less than the wall thickness of the copper coil. So 0.03. And the other boundary layer is for the water. Because of the no-slip condition, we will have a very large velocity gradient next to the inner wall of the coil. So you can build it to see how it looks like. We will need only 2 layers for the water. And then insert a swept node to sweep this mesh surface along the coil. So select domain and choose the coil-water combination. Insert a size node. And finally, we need to mesh the air domain. I will use a free tetrahedral mesh element for that. So under mesh, insert free tetrahedral and keep it as remaining, and then click on build all. So usually when you need a very dense mesh and you're working with a multiphysics problem, it's always advisable to use a user-controlled mesh, because that will, if you build it properly, it will be more efficient than generating an automatic mesh. So now the mesh is complete. You can hide some surfaces to see the mesh inside. You can see that we have a swept mesh. The same surface is repeated multiple times. Now we need to insert the study. So under study 1, we need 2 steps. The first one will be the coil geometry analysis to compute the flow of electric current in the coil. Make sure that only magnetic fields is selected, and the other one is frequency domain. Insert the frequency and unselect laminar flow and heat transfer. So you could possibly model all the three physics interfaces together, but that will be computationally very expensive. So what I'm doing is I'm using a frequency domain to compute the magnetic field's physics. That will allow us to get the average power dissipated in the coil over a single cycle. So a sinusoidal current input will go into the coil, and that will dissipate heat into the coil due to Joule heating. And we want to know how much is the average power dissipated over a single cycle. And then that value or that solution will be transferred into another study, which will compute the laminar flow and heat transfer together. So right-click on study and insert the default solver. Make sure that all the appropriate solvers are selected. In this case, everything seems to be fine, so click on compute. After this study is completed, I will insert another stationary study in which both the laminar flow and the heat transfer physics will be computed. And that will use the solution from the frequency domain study. So basically, we need a stationary study to get the temperature distribution in the coil, which means if you are planning to keep the induction heating coil turned on for a long time, and when I say a long time, let's say a few minutes, without any water flowing through the coil, it can really heat up. It can reach a temperature above 100 degrees, which means it can cause skin burns if you accidentally touch it. So we want to know whether if you keep the induction heating coil turned on for a long time, will the water flowing inside it keep it sufficiently cool? Okay, so the study is completed now. Go under study and insert a stationary study. Unselect magnetic fields because only the laminar and heat transfer physics will be solved. And before clicking on study, there is one extra node I need to add in heat transfer because we need to transfer the solution from the frequency domain to the stationary study. So under domain, we need to select heat source, select coil, and then the heat source, it will be user-defined. Do not choose volumetric loss density because we are not computing the magnetic fields physics simultaneously with the heat transfer physics. Instead, we will use an operator which is called withsol, which means it uses a solution, and we need the solution tag, which you can get from under the frequency domain study. You can see that SOL1 within the brackets. This is the solution tag. So you need to insert the solution tag, and you need to insert the variable which you want to transfer. So in our case, we want to transfer the power dissipation. So that variable is called mf.qh. If you do not know this name, you can even get it under the results. All you have to do is insert a 3D plot group, and then volume. Click on replace expression, and then you can go to magnetic fields, and you will find a whole bunch of properties under which heating and losses you will find mf.qh. It's the volumetric loss density. So that will be the heat source, the radiation, the convection, and the water will be removing heat from the coil, and the electric current will be supplying heat to the coil. Right-click on Study 2 and insert the default solver. Okay, I'm getting a warning. There is no feature constraining the pressure. Right, so I forgot one node in the laminar flow interface. Under physics, we need to constrain the pressure also. So we specified only the inlet. We also need to specify the outlet. Select the other end of the coil. And we will assume that the coil will be exiting into the tank at the ambient pressure. So keep the relative static pressure as 0. So this is 0 relative to the atmospheric pressure. Okay, under stationary solver, insert fully coupled. You can keep it as segregated solver if you do not have enough memory in your computer, but if you do have enough memory, it's better if you select fully coupled so that the physics and so that all the physics interfaces are solved simultaneously. And activate or enable the direct solver. Change the solver type to Paradiso. And with that, we are ready to compute the solution. The laminar flow will be highly nonlinear, which means many iterations will be taken to compute the solution. So I expect that this will take between 5 to 10 minutes. So I will pause the video, and when the solution is completed, I will resume. Okay, so there was a problem. I think I forgot to insert the tag number from the frequency domain solution. So it is sol 1. Sorry about that. Now we can click on compute. Everything should be okay now. Okay, so the solution seems to be working fine now. So I will pause the video and I will return when the solution is completed. Okay, so the solution has been completed. You can see it has taken 11 iterations to converge. And now we can look at the results. So let's look at the temperature distribution. From dataset, you need to select study 2. Insert volume, and we will select temperature T. Okay, so the ambient temperature was 22 degrees Celsius, and you can see the maximum temperature is about 22.7. It's only 0.7 degrees increase. That's with the flow of water inside the coil. If you turn off the laminar flow interface in this study and recompute the study, you will find out that the temperature of the coil, the maximum temperature, can reach around 120, 140 degrees. That's if you only keep radiation and convection without heat transfer to the water. So that high temperature is enough to burn a human's skin. So the water flow inside the coil is very beneficial in this case. You can also plot the velocity profile of the water if you wish to. Select study 2, volume, and we will search for velocity and select velocity magnitude. Okay, so what you see in blue color is 0 because of the wall. But at the center of the flow, You can see that the velocity can reach up to 2 meters per second. You can also plot the pressure of the water. So it starts with high pressure and the exit is close to 0 because that's what we selected. And if you want to plot some parameters related to the coil, you can also do that. Under derived values, you can select global evaluation, keep the dataset for study 1. And you can plot parameters such as variables such as the power dissipated. So that's given by P coil. You can check the impedance of the coil. You can also check the current. So this is the power dissipated as heat in the coil. So it's about 10 watts. You can see that the real component of impedance is very low. That's because copper has a very low electrical resistance. If you use a material like iron in the coil, then the real part of the impedance will be about 10 times higher, so much more power will be dissipated. So yeah, that's all for this simulation. For a real induction heating coil, if you have more number of turns or if you have a different material, you can study the effect of water velocity in the coil. How does water velocity affect the heat transfer and the temperature distribution in the coil? So the concepts I illustrated in this simulation can be used in multiple ways to design an induction heating coil. If you have any questions or if anything is unclear in the physics or anything that I've done in this simulation, feel free to leave a comment. And thank you for watching this video.